We've already learned about some differentiation techniques, that is, ways that we can take derivatives of functions. So for example, we've learned about the power rule, the extended power rule, the product rule, and the quotient rule. We've also seen that a derivative tells us the rate of change of one variable with respect to another variable. Now none of that is going to change in what we're going to talk about now, when we talk about higher order derivatives, because we're building on what we already know. So we know that if we have a function, that we can take a derivative of it, which we're going to call a first derivative. And just as before, that first derivative tells us something about the slope of the tangent lines to this curve. But now we're going to look at something called a second derivative. A second derivative is just the derivative of the first derivative. So the derivative of 5x to the fourth minus 12x to the third plus 1 is 20x to the third minus 36x squared. We're still using our same power rule that we learned before, but because we're applying it to the first derivative, we now are looking at a second derivative. A second derivative tells us about the rate of change of the slope of the tangent lines to the curve. In other words, how fast are the slopes changing as we move along the curve from left to right. As far as notation goes for a second derivative, some of it's very easy to write, like y double prime or f double prime, but you'll find that some of the notation for second derivative looks a little more complicated. What's really important is that you recognize that all of these things are asking us to find a second derivative. So let's practice finding a second derivative. Let's suppose we have a function y equals 1 over x, and we want to find its second derivative. Well, first we'll have to take the first derivative, so we'll need to rewrite the function in a way that we can use one of our derivative rules. So if we rewrite y equals 1 over x as y equals x to the negative first power, then we can use our power rule to take the first derivative. But we want the second derivative, so we'll take the derivative of the derivative, which is 2x to the negative third, or we could rewrite that as 2 over x to the third. So what if we have a function that looks like this, x over x plus 1, and we're asked to find f double prime of 2. That means we want to find the second derivative of our function and evaluate it at 2 by substituting 2 for all of the x's. So we'll need to take a first derivative first, and since this is a quotient, we'll need to use our quotient rule. Now there have been times when we've used the quotient rule and we've said that there's no need to simplify, but in this case we definitely want to simplify because we're going to have to take a derivative of this derivative, and right now it's a very complicated looking function. So if we simplify our first derivative, now we have something that we can maybe rewrite so that we can use our power rule to take a derivative of the first derivative. So if our first derivative is x plus 1 to the negative 2, the derivative of that derivative is negative 2 times x plus 1 to the negative 3 times the derivative of the base, the derivative of x plus 1 is 1. And if we simplify that to negative 2 over x plus 1 to the third, we'll find that it's easier to finish this problem, because we want to evaluate this second derivative when x is 2. So if we substitute 2 in for the x in our second derivative, and then simplify using order of operations, we'll find that f double prime of 2 is negative 2/27. Derivatives can be used to describe the motion of an object. So if we say that s of t is the distance of an object from a starting point at time t, then the derivative of that, which we can call v of t, is the velocity of the object at time t. It's the speed that the object's moving. And the second derivative of our function s of t, which is really just the derivative of the velocity function, is the acceleration function a of t, the acceleration of the object at time t. Here's an example that uses that relationship between position, velocity, and acceleration. A pebble is dropped from a hot air balloon. Find how far it has fallen, how fast it's falling, and its acceleration after 3.5 seconds. Let s of t equal 16t squared, where t is in seconds and s is in feet. So s of t is a position function. It tells us something about how far the pebble has fallen after a certain number of seconds have passed. And we want to know how far the pebble has fallen after 3.5 seconds. So we need to find the value of our function s of t when time is 3.5. So if we substitute 3.5 in our position function and use order of operations to simplify, we'll find that the distance that the pebble has fallen after 3.5 seconds is 196 feet. We also want to know how fast the pebble is falling. So we'll need a velocity function for that. The velocity is just the derivative of the position function. So the derivative of 16t squared is 32t. That means if we want to know how fast the pebble's falling after 3.5 seconds, we want to know the value of the velocity function when t is 3.5, which is 112 feet per second. The third thing we're asked to find is the acceleration. And the acceleration function is the derivative of the velocity function, which is also the second derivative of our position function. So the derivative of our velocity function, which is 32t, is just 32. To find the acceleration at 3.5 seconds, we substitute 3.5 into our acceleration function for t. But there isn't a t in that function, it's just a 32. It's a constant function. So the acceleration is a constant value of 32 feet per second squared. It's not surprising that our acceleration function is a constant because gravity is what causes acceleration. And gravity will accelerate objects at a constant rate of 32 feet per second per second. So let's start with this function. It's a third-degree polynomial function, and we're going to think about what happens along the graph of this function. Where is the slope of the tangent line to this function equal to 0? Well, that happens in two places. There's 2 points on this curve that have tangent lines that are horizontal, that have a slope of 0. The first one is a point that we call a local maximum. That means that right around that point, it's the highest point there is. It's kind of like being at the top of the hill. It doesn't necessarily mean that it's the highest point on the whole graph. In fact, it definitely isn't the highest point on the whole graph. But right around its little neighborhood, it's the highest point. So it's a local maximum. And the other point where the slope of the tangent line is equal to 0 is this one, which occurs at what we call a local minimum. That means right around that point, we have a low point on the graph. It's like being at the lowest point of the valley. It's definitely not the very lowest point on the entire graph, but right around its little neighborhood, it is the lowest point. We would say that this function has 2 places where it has relative extreme points. Those are places where the first derivative is equal to 0. Where are the slopes of the tangent lines to this curve positive? Well, there are lots of tangent lines that we could draw that have positive slopes. In fact, all along the part of this curve that we've marked in blue, we could draw tangent lines that have positive slopes. And in fact, over here, we could also draw tangent lines that have positive slopes. So anywhere along this part of the curve that's marked in blue, we have tangent lines with positive slopes. Now imagine that we have a point on the curve and we move it from left to right along the curve, only along the blue part. You'll notice that the point is also moving up. And if we do the same thing on this blue part of the curve, where the tangent lines had slopes that were positive, we move the point from left to right, it also goes up at the same time. So what we can say is that the function is increasing where the first derivative is greater than 0. The function is increasing where the tangent lines have positive slopes. So where on this curve are the slopes of the tangent lines negative? Well, once again, there's lots of different tangent lines we could draw that have negative slopes, and all of those tangent lines touch the curve somewhere along the red part of the curve. Imagine that you have a point that you move along the red part of this curve from left to right. The point would also move down. So we would say that the function is decreasing where this first derivative is less than 0. The function's decreasing where the slopes of the tangent lines to the curve are negative. So let's put this all together. The function has relative extreme points where the first derivative's equal to 0. The function's increasing where the first derivative is positive, greater than 0. And the function is decreasing where the first derivative is negative, where it's less than 0. Now stop for a second and think about what happens on either side of those points where we had a relative extreme point, where we had a relative maximum or a relative minimum. You'll see that on either side of the relative extreme points, the first derivatives were changing signs. They were either changing from positive to negative or from negative to positive. That's going to be something that will be really important to help us graph functions. Now that number where we saw a change happening in the first derivative is something that we call a critical value. So a number c is a critical value of a function f if the function exists at that point and the first derivative is either equal to 0 or the first derivative does not exist at that point. The first derivative is undefined. So you might be thinking, why does this matter? Well, it's because we'll be able to find those extreme values because they're always going to be critical values for a function. But the critical values will not necessarily be extreme values. So when we're graphing functions, we're going to be looking for critical values because they might be extreme values. So we'll have to come up with some ways to test to see if those critical values are extreme values. So let's go back and look at this very same function. We already know what the graph looks like because we started with the graph. And let's pretend that we didn't know what the graph looked like and we had to come up with some way to graph it based on the information we were getting from derivatives. So the first thing we're going to do is find any critical values for the function. Critical values occur where the first derivative of the function is either equal to 0 or undefined. So if we take the first derivative of the function, it's a polynomial function, so the first derivative is defined everywhere, but is the first derivative ever equal to 0? Well, we'll set it equal to 0 and do some factoring, and we find out that there are 2 points, 2 values for x, where our first derivative is equal to 0. So these are considered critical values for the function. Our second step is to take a look at the sign of that derivative in the intervals defined by the critical values. This is called the first derivative test. The two critical values divide our number line into three parts. The first part is from -infinity to -1. The second is from -1 to 2. And the third is from 2 to infinity. Now, to organize the information that we're going to get from the first derivative test, we're going to make a table that shows those three intervals. And we'll need to pick a number out within each of the intervals to use as a test value. So for example, -2 is a number that's in the interval from -infinity to -1. 0 is a number that's between -1 and 2. And 3 is a number that's somewhere between 2 and infinity. You can pick any number in the interval for the test value. Now what we're going to do is look at the sign of our first derivative in each of those intervals using the test values. So our first derivative, remember, was 6 times x minus 2 times x plus 1. For the first test value of -2, f prime of -2 would be 6 times -2 minus 2 times -2 plus 1. Now we could get an actual value for this, but we're really just interested in the signs. So you can usually simplify the arithmetic if you just think about the signs of the factors. So for example, 6 is definitely positive. -2 minus 2 is negative, and -2 plus 1 is also negative. So what we have is a positive number times a negative number times a negative number, which gives us a positive result. For 0, we'll substitute 0 into the first derivative. So we have 6 times 0 minus 2 times 0 plus 1. Once again, I'm only interested in the sign of the derivative. So I'll say, well, 6 is positive, 0 minus 2 is negative, 0 plus 1 is positive. So we have a positive times a negative times a positive, which is negative. And for 3, we would have 6 times 3 minus 2 times 3 plus 1. 6 is positive, 3 minus 2 is positive, 3 plus 1 is positive, and a positive times a positive times a positive is positive. So what I have now are the signs of the first derivative, which tells me about the slopes of the tangent lines, and it tells me if the function is increasing or decreasing in that interval. So what I know is that in this first interval, from -infinity to -1, the function's increasing. From -1 to 2, since my first derivative is negative, my function is decreasing. And from 2 to infinity, my function must be increasing because my first derivative was positive. That also tells me that I must have a relative maximum at x equals -1. Because if my function's increasing and then decreasing around -1, I must have a high point on my curve. And at 2, I must have a relative minimum, because my function's decreasing and then it's increasing around 2. So now we're going to find the y-coordinates of those two extreme points we found. So this is the information we have. We know that we have a relative maximum where x is -1 and a relative minimum at x equals 2. This is our function. And remember, the function is a relationship between the x and y coordinates on the curve. So we have one relative maximum where x is -1. To find the y-coordinate that goes along with that, we can substitute 1 into our original function. and we get a y-coordinate of 19. So that relative maximum is at -1, 19. The relative minimum has an x-coordinate of 2. So to find the y-coordinate that goes along with that x-coordinate, we'll use 2 as the input for our x and our function, and our output's -8. So we have a relative minimum at 2, -8. So now we can finally graph the function, but we're going to need just a little more information. We know there's a relative maximum at -1, 19. We know there's a relative minimum at 2, -8. And we know that our function's increasing to that relative maximum, decreasing to the relative minimum, and then increasing after that. Now obviously the function isn't a zigzag. It's got some more curves to it. So to figure out what those curves look like, we're going to find a few more points. So we'll pick some values for x that are around these points we've already found. We know what happens when x is -1. That's our relative maximum. We know what happens when x is 2. That's our relative minimum. So we pick some x values that are a little less or a little more than either of those x values. And once we've got those points, we can graph them. And now we've got a little more to work with. We've got some subtle curves going on that we can connect to make our final graph. So we're going to develop some other techniques in our next lesson that will help us figure out more about those subtle curves along a graph. But even with what we've done so far, we've got a really good idea of how we can graph a lot of functions by using derivatives.